Let's move closer to ocean circulation now. We have been just introducing different concepts and relations to, or parallels to atmosphere. Let's look at some of the observed circulation. Okay, this is a typical profile of the annual mean temperature and salinity at 50 west, 30 north in the Atlantic, which is not quite typical because the Atlantic is very different than the Pacific, as we said. And you can see that the temperature is warm near the surface. The thermocline is not so strong, or let's say the mixed layer is hardly visible. The temperature is almost continuously decreasing and then reaches this near constant temperature of about 2 degrees as we go beyond a couple of kilometers. Okay, so there is a thermocline, but it's not very sharp like in the low latitudes, and the mixed layer is not well defined because at these latitudes you have heating in the summer that's not very strong at this latitude, and you have a cooling in winter that can be strong depending on the various storms and so on. But the salinity also shows different behavior compared to what we saw before in the mixed layer. Has a continuous drop from about 37 or so PSU. PSU here is practical salinity unit. It's a non-dimensional number, which is basically a measured quantity which corresponds to conductivity of the water. Okay, you can think of it as parts per thousand as well, but the most scientific way is to think of it as PSU. Okay, so it's going down to about 35 point something and then becoming constant at about 35 in the deep ocean. Okay, we can look at various depths as well. This is now the annual mean temperature profile near the surface. You will see at the same latitude and longitude a fairly strong seasonal cycle. As I said, the winter months and the convective cooling because of the winter storms and colder air temperatures brings the temperature down by several degrees, 4 degrees, which is much higher if you go at the same latitude at another longitude in the Pacific. Okay, so there is a summer warming, fall warming, and cooling into the winter. But if you go deeper, just at 500 meters, then the temperature has no seasonal variations. So atmospheric forcing is getting trapped in the upper ocean. This is very critical. All the forcing of the deep ocean is going to come from these density-driven drop of heavier waters into the deeper ocean, and the subtropical gyres where the wind forcing can go deeper than in the upwelling region, and so on. So the thermocline mostly gets shielded from the atmosphere in that sense. Okay. Nonetheless, you have strong circulation at the surface because of the winds constantly dragging the ocean around. This is a figure that's hardly visible, but these are currents derived by using the so-called drifters in the ocean. For years and years, Peter Neeler used to release these drifters, which are basically like a ball with a drogue below, which follow the current, and they have a beacon that transmits data to the satellite and so on. So you will see some general features which are much better visible here. This is from Encyclopedia Britannica. You will find many such figures on the internet. Okay, so you have trade winds that are pushing waters westward, northeast and southeast trade winds, creating the Pacific South Equatorial Current, Pacific North Equatorial Current. You can think of these as the trade wind equivalent of the ocean currents. Also exist in the Atlantic Ocean, but very different in the Indian Ocean. Okay, so there is a current going exactly opposite to the winds in the deep tropics. What is happening? It turns out that as you drag the water west and you pile it up here, there is a density or gravity driven current down the hill. And remember, you're in the northern hemisphere, so if you're going to the east, Coriolis will push you to the right into the equator. Equator is a dynamical boundary. You cannot cross it easily because Coriolis changes sign across the equator, which means an eastward going current can remain quite coherent because the Coriolis will keep it pushed up against the equator in a crude sense, okay? Whereas the currents that are going westward are constantly being diverged towards the poles. Okay, so constant energy from the winds is keeping these currents going westward. The waters pile up here and so on. And there are reasons why you get strong, warm currents, strong, narrow, deep, warm currents on the west, whereas you get more diffuse, shallow, cold currents coming down here on the east. Obviously, westerlies and northeasterlies create a clockwise circulation, but the trick is to explain why the currents are strong, narrow, and deep here, whereas they are weak, broad, and shallow here. The same thing here. Okay, so you know the Gulf Stream, probably heard of it, and you can see that it goes all the way out into the Greenland, Norwegian, Iceland seas, whereas the Pacific looks very different. It has some exchange with the Arctic here. This also has exchange with the Arctic. So you get very strong zonal contrasts here. We will see later on that the temperatures here can be 10, 20, 30, even 50 degrees colder than the same latitude here over Ireland and the UK. The climate is also very different. Cold, miserable winters, whereas drizzly, warmer winters here, and so on. So the ocean, because of its high heat capacity, is able to control and modulate weather and climate around the world. The Southern Ocean is obviously different because it's a continuous channel. Indian Ocean is different because the currents completely reverse, because the winds completely reverse north of about 5 to 10 south, the monsoonal circulation. Okay, so complicated circulation in the Arctic. It's almost an enclosed basin. There are lots of gyres happening within that, but outside that we have the large subtropical gyre and the subpolar gyres, clockwise and counterclockwise, and so on. So cyclonic and anticyclonic circulation, high pressure, low pressure, same concepts we had in the atmosphere work in the ocean as well. We will see more details of these currents as we go along. I'm just laying the groundwork for the dynamics by looking at the general features of the ocean and its circulation.